Hello everyone, welcome to this lecture. So in this lecture, we'll give a sketch of proof of Hopf's theorem of rotation index of a simple closed planar curve. Okay, so let me first write down the statement. So let us take gamma be a simple closed regular plane curve. So plane curve means it is in the image of the curve, it lies in R2. So then the rotation index of gamma is either +1 or it can be -1. Okay, so what do you mean by a simple curve? So simple curve means it does not self-intersect other than the endpoints. Okay, so now let us try to prove this thing. So we can always have a parameterization of this gamma, which is unit speed. So in order to do that thing, so what you do, so you take the arc length reparameterization of this gamma. Okay, so let gamma defined on this interval 0 to L. So this map is be the arc length parameterization of gamma. Okay, so then this gamma, it will be a unit speed curve. So it will be something like this. Okay, so this is my gamma. And so now what I'll do, so suppose I take a horizontal line segment. So take some horizontal line segment which does not intersect this gamma. So this is my gamma. So suppose this is my orientation of this gamma. And take any line segment which is parallel to x-axis, something like this. Okay, and you move this line segment towards this gamma, and you will get a point where this point on gamma, so where we'll get a line which is parallel to the chosen line, this one. Suppose this is my L. And if I displace it parallelly, so I'll get a line capital L, which will intersect gamma at a single point. In fact, this capital L, it will be tangent at some point P of this gamma. Okay. So now without loss of generality, I can take this P to be my origin. Okay. Because if I change this gamma by a translation, so the curvature remains the same and also the rotation index, it remains the same. Okay, so without loss of generality, I can assume this P to be my point origin. Okay, and also I can assume that gamma 0 is 0, 0. Okay, so let me write this statement. So without loss of generality, So we can assume gamma 0 is equal to 0, 0, and gamma dot 0 is along the x-axis. So let us assume, so this gamma dot 0 be the unit vector 1 comma 0. Yeah, so gamma dot 0, it can be either 1 comma 0 or minus 1 comma 0. Okay, so let us take this gamma dot 0 to be the unit vector 1 comma 0. Okay, so now what to do? So you want to prove that the index of rotation index of this gamma is either +1 or -1. Okay. Okay. So now, so what I'll do, I'll define a map as follows. So let psi s comma t is equal to gamma s minus gamma t divided by norm of gamma s minus gamma t. Yeah. So when, so this, so s is not equal to t. So s is not equal to t, and okay, maybe I'll just write more precisely. And st, it is not equal to 0L. Okay. And uh, okay, so what I'm doing here, so this psi, it is defined on this triangle as follows. Yeah, so let me draw this triangle. So this is my 0, 0, this is my 0L, and this is my L comma L. Okay, so here it should be S less than T less than equals to L. Okay, so psi is defined on this triangle as follows. So this is the definition of psi, and it is equal to gamma dot S. Okay, if S is equal to T. Okay, and I have to define psi of 0L. So this is defined to be minus gamma dot 0. Okay, so this is my definition of the psi. So psi is called second map. Okay, so what I'm doing here, so suppose, so this is my gamma s, and this is my gamma t. So what you do, so you join this gamma s and gamma t by a straight line. And now take the vector gamma s minus gamma t, and you normalize it. Okay, so that after normalization you will get a unit vector. So that's why it is called second map. Okay, and if s is equal to t, so you'll get a tangent vector. Okay, so if s is equal to 2, you will get a tangent vector. Okay, so here one mistake I have made. So this should be gamma t minus gamma s. So divided by gamma t minus gamma s. So then this direction, it should be in the other way. Yeah. Okay. So now if s is equal to t, so we have this tangent vector here, unit tangent vector. Okay. All right. So you can check that this map psi is continuous. So this map psi is continuous. So let me draw it again. So this is my gamma, and I have the second map psi. All right. Now let us take any element, take any point on this gamma. So let us take this point here, and let us take another point. So this is my second, and if I take the unit vector at this point, so this is my unit vector. So E1, so E1 is 1 comma 0, and this vector, so let us call it to be psi st. Okay, so we'll get a unit vector here corresponding to this vector. So we'll get a unit vector, and let us take the angle between the unit vector and psi st to be theta st. Okay, so let theta st denote the angle between psi st and the unit vector 1 comma 0. Okay, all right. Okay, so now note that so theta, so what is theta s? So theta is what? Okay, so before that, so what is my psi s comma s? So this, as per the definition, it is gamma dot s. Okay, and gamma, it is a unit speed curve. So this gamma dot s, it will be equal to cos phi s comma sine phi s. Okay, so where phi s is the turning angle of gamma at gamma s. Okay, all right. Okay, so therefore uh, so theta s comma s. So this will be equal to your phi s. Okay. So now recall. So what do you mean by rotation index? So rotation index, it is an integer. So 2 pi times the rotation index of gamma. So this is equal to phi L minus phi 0. Okay. So what you have to show that this phi L minus phi 0, so this will be equal to your 2 pi. So if I prove this thing, so then the rotation index of gamma, it will be your plus 1. Okay, all right. So now phi L minus phi 0, so this is equal to theta L comma L minus theta 0 0. So which is again equal to theta L comma L minus theta uh, 0 L plus theta 0 L minus theta 0 0. Okay. So I have this thing here. Okay. So now let us first take this thing. And then after that, we'll compute this part. Okay, all right. Okay, no, first, so let us take uh, this thing, okay, and then we'll compute this second part, okay. So theta 0 L is the, so theta 0 L is the angle between uh, psi 0 L and the unit vector E1, okay. Okay. So now, so observe that. So what is my gamma, sorry, psi is L. So this will be equal to gamma S minus gamma L. Sorry. So as per the definition, it will be gamma L minus gamma S divided by norm of this. Okay, so let me draw the picture again. Okay. So at this point, so theta 0 0 is equal to phi 0. So which, so we have taken it to be the following. So this gamma dot 0 is equal to 1 comma 0. Okay. So this is my unit vector E1. So this in fact is the tangent vector at this point. Okay. So therefore, so this theta 0 0, which is again equal to phi 0, is equal to your 0 here. Okay. Okay. So now what we are doing, so if you go back to this picture, So now we are taking this line segment. Okay, so now we are taking a point here. So this is my S comma L. Sorry, so this is point is my 0 comma S. Okay. So what is psi of 0s? It is gamma s minus gamma 0 divided by norm of gamma s minus gamma 0. Okay, so where this s is not equal to 0. Okay, so if I have this thing, so this is my point gamma s, and I am taking this line segment joining this two. Okay, and then you normalize to get a unit vector. Okay, so if I do that thing, so I'll get a circle like this. Yeah, so we'll not get this circle, so we'll get a unit circle, something like this. Yeah, so this is my unit vector, so we'll get a circle like this. Okay, so corresponding to this vector, so we'll get a point here in this unit circle. So corresponding to this point, so we'll get a point here. Okay, so this is basically my psi 0s, this point. Okay, so we are getting this point here, and this angle is theta 0s. Okay, all right. Okay, so now, so what you do, so take s tends to L. Okay, so then so if I take s tends to L, so what you'll get, so psi 0L is what? So psi 0L is gamma L minus gamma 0 divided by gamma L minus gamma 0. Okay, so no, sorry. So we have defined this psi of 0L to be minus of gamma dot 0. Okay, so yeah, so that's why we have defined it this way. So this will be minus of this gamma dot 0. Okay, all right. So initially at 0, 0, so you have this vector E1, and then so we are tending this S tends to L. So what we are getting here, so this, so we are getting this thing. So this is my psi of 0 comma L. Okay, so this is basically minus of E1. Okay, so therefore, so this implies that theta 0L, so this is equal to pi. Okay, so this is equal to pi. Okay, and now similarly, so what you can show that uh, theta L comma L, so this will be equal to your 2 pi. Okay, so how do you show this thing? So now you pass on to the second bracket. Okay, uh, so you look into theta uh, just 1 minute. So theta L comma, yeah. So you want to prove that theta L comma L is equal to 2 pi. So what you do, so now, so you take this line segment. Okay, so you take psi S comma L. Okay, and you, okay, so instead of taking theta ls, so you take theta s comma l. Okay, so in order to find theta ll, so what you do, so now you take psi s comma l, so it is your gamma l minus gamma s divided by gamma l minus gamma s. Okay, so this gamma L, it is again equal to your gamma 0, which is my origin. So you have minus gamma S divided by norm of gamma S. Okay, and now so take S tends to L. Okay, so now what you are getting here, so we are getting, so we'll be getting this vectors. So this is my psi S comma L. Okay, so this implies that, so theta L comma L is equal to your 2 pi. So therefore, 2 pi time rotation index of gamma is equal to theta L comma L minus theta L comma 0 plus theta L comma 0 minus theta 0 comma 0. So this is equal to 2 pi minus pi plus pi minus 0. Okay, so this is equal to 2 pi. So this implies that rotation index of gamma is equal to your plus 1. Okay, so if gamma dot 0 is equal to minus E1, so then similarly, what we can find that rotation index of gamma is minus 1. Okay, so this is the proof of Hopf's theorem. Okay, so we'll stop here.